Okay, 1451. Okay, here we have a car. Sports car. It has a mass of 2.3 megagrams, 2,300 kilograms, and accelerates at 6 meters per second squared, starting from rest. If the drag resistance on the car, okay, remember drag is kind of a wind resistance as the car is moving forward. There's this drag resistance, wind resistance that wants to slow the car down. The drag resistance on the car due to wind is this, okay? Fd is 10 times velocity newtons. So this drag force is a function of velocity, where V is the velocity. Okay, determine the power supplied to the engine. Now this is important. Power to the engine. Okay. Okay, maybe I'll chat about that in a minute. So not power supplied by the engine, but power to the engine. Power to the engine. Power supplied by the engine is also very important. So power supplied by the engine. Okay? So these are two important things to understand. If you have an engine or you have a motor, okay, just imagine this is an engine or a motor. Remember that a motor or an engine has an output power, and it also requires an input power or input energy, okay, and output energy. Okay? So you need to distinguish between the two, and this is where mechanical efficiency comes in. Mechanical efficiency is P out over P in. It's how much power or energy can you get out of the system after you've put in a certain amount of power or energy. And remember that you can never ever get the same or more or the same out that you put in. You will always lose energy or power because of friction, for example, and so there's always going to be losses in the engine. Okay, but remember, we're looking for how much do you need to put into this engine if this is the case, okay, based on all this information. Okay, so determine the power supplied to the engine when time is 5 seconds, and then we have a mechanical efficiency of the engine of 0.68. Okay, so again, I'm dumb. I don't know how to solve this problem. It says determine the power. That's the question. Okay, what's power? Power is, I'm going to write it F dot V. Okay, that's a good starting point. Now ask me what the power is. Okay, that's what I know. Power is force times velocity. But remember, it is the force, the component of the force in the direction of the velocity that we need to put here. Okay, if we convert it into scalar form. Okay, so do I have velocity information? No. Do I have force information? Let's just go and have a look at, first of all, the force information. Okay, so let's come have a look over here. Sum of the forces in the X is mass times acceleration. Okay, now we need to draw the free body diagram. If there's our car, remember that the drag is opposing the direction of motion. But now, what is actually causing the car to accelerate in that direction? What is it? Well, many students would say to me it's the force of the engine. Okay, so the engine force, which is, it's true, but it's not technically true. Because you can have the engine rotating, okay? You can have some output from the engine, but the car's not moving, okay? And to cut a very long story short, guys, what happens is the engine rotates the wheels, okay? Actually, if it's a front wheel drive, it rotates the wheels, and if this car is going in this direction, what is the direction of the wheels, the rotation of the wheels? If the car is moving this direction, is the wheel rotating like that, or is it rotating like that? Okay? So we know that the wheel will be rotating like that. So, if the wheel is rotating like this, and there is the road, in order for this car to move forward, there needs to be a friction force acting on the wheel in that direction. Okay? Static friction. So we know that we have a F friction force. Okay? Frictional force that is actually transmitting the output power from the engine onto into this contact point and actually propelling the car forward. Okay, so friction is acting at the wheel. So those are our two forces in the X direction. We have this F, okay, I've called it F friction, but that's there, F minus 10V, which is this drag force, is equal to the mass times acceleration in the X direction, which is 6. So what happens is now we get this force, this friction force, this force that is propelling the car, right? Actually, this is the force that we're looking for, okay? Initially, all right? So now we have this force as a function of velocity, but what we're looking for is that velocity. So we can get this force and multiply it by the velocity, okay? So we can just use this equation over here. Acceleration was given as 6 and the time is given as 5. So the velocity after 5 seconds with 6 meters per second squared acceleration is 30. All right. Now I want to come back to this idea of P out and P in, because what we've calculated, if I say now P is the force, which is this 13.8 10 to the 3 plus 10 times 30, okay, Newton, what power, that's the force, times 13 meters per second, right? That's P equals F times V. But what power is this? This is the out power, the P out, the power that the engine supplies to the vehicle, okay? But what are we looking for? We're looking for P in, all right? And we know that efficiency is P out over P in, so P in is P out over 0.68, okay? So that's exactly what we've done here. This is my P out equal to that. I need to divide it by the mechanical efficiency to get my P in. This is how much power needs to be supplied to the engine. Okay? Okay, so I hope you get that. And is this answer correct? Yes, it's correct, because the P in is always greater than P out. You can never get as much out as you put in. Okay? Hope you learned something.